Hi, hello friends, welcome to our channel Study of Mathematics. Hi friends, in this video we will discuss the other theorem in the chapter Matrices. Theorem is 3.5.6. The statement of the theorem is if A equal to A1 B1 C1, A2 B2 C2, A3 B3 C3 is a non-singular matrix, then A is invertible and A inverse equal to adjoint A by det A. This is our given theorem statement. In this theorem statement, we have to given a matrix of order 3 by 3 and also given A is non-singular. Non-singular means determinant of A is not equal to 0. Then we already know the invertible matrix definition. Determinant of A is not equal to 0, then A is invertible. Then by using that definition, we can say that A is non-singular, that is that A is not equal to 0, then A is invertible. Now we have to show A inverse equal to adjoint A by det A. Adjoint A by det A. In this, next we will go to proof. First write down the given matrix. Given matrix is capital A equal to A1 B1 C1, A2 B2 C2, A3 B3 C3. This is a 3 by 3 matrix. If a matrix is invertible, then we have some of the conditions are that a matrix is a square matrix and also it is a non-singular matrix. Then that matrix is invertible. By using that, here given matrix is a 3 by 3 matrix, then A is a square matrix and also given A is A is non-singular, then A is also invertible and that A is not equal to 0. And given that A is not equal to 0, then automatically A is invertible. By the definition of adjoint of A, by definition of adjoint of a matrix, by the definition of adjoint of a matrix, we can write adjoint of A is equal to the matrix is, here adjoint of A is means the transpose of a matrix which is formed by the cofactors matrix of A. That means first we have to find out the cofactor matrix of A and then transpose. Then the transposed cofactor matrix is called the adjoint of A. Then adjoint of A equal to A1, A2, A3, next B1, B2, B3, C1, C2, C3. Here A1, A2, A3, B1, B2, B3, C1, C2, C3 is the cofactors of each element of a matrix A. Then these are the A matrix and adjoint of A matrix. Now next we have to find out A into adjoint of A. A into adjoint of A. For the proof of this theorem, we have to first find A into adjoint of A. Then that is matrix A into adjoint of the matrix A. That is equal to, first matrix A is A1 B1 C1 small letters, A2 B2 C2 and then A3 B3 C3 into adjoint of A means capital A1 capital A2 capital A3 B1 B2 B3 C1 C2 C3. Now we have to find the product of this matrix. Then that is equal to first row with first column a1 small a1 capital A1 plus b1 b1 plus c1 c1. First row second column a1 a2 plus b1 b2 plus we have to calculate in this side. The lengthy process, then that is equal to matrices of a1 a1 plus b1 b1 plus c1 c1, and here a1 a2 plus b1 b2 plus small c1 capital C2. And then third element is a1 a3 plus b1 b3 plus c1 c3. Similarly, second row first column a2 a1 plus b2 b1 plus c2 c1. Second column a2 a2 plus b2 b2 plus c2 c2. And then third element is second row a2 a3 plus b2 b3 plus c2 c3. Finally, third row first column a3 a1 plus b3 b1 plus c3 c1, a3 a2 plus b3 b2 plus c3 c2. Here capital C. Next a3 plus b3 b3 plus c3 c3. This is the multiplied matrix. We know that determination of a1 b plus b1 b1 plus c1 c1 is the determinant of a value. That is determinant of a. That a value is a1 a1 plus b1 b1 plus c1 c1, and by the definition of det A, this is written by using the definition of det A, and by using the properties of a determination and the last ninth property, that is the a1 a2 plus b1 b2 plus c1 c2 value is equal to 0. The property is that in property by the ninth property of a determination of a matrices, by using that this value is equal to 0 and third value is also 0. A to A1 value is 0. Here this is also the determination. Determination by using the second row. Determination by using the first row. Here determination by using the third row. This value is also det A. 0, 0, 0, det A. Here we have to common det A value. Det A into 1 0 0 0 1 0 0 0 1. This is nothing but a unit matrix or identity matrix. Det A into capital I. Det A into capital I. That means here we have to find A into adjoint of A. A into adjoint of A value is det A into I. From this we have to write down A into adjoint of A by det A. Here we can cross multiply the value or taken determinant A is in multiplication form by taking in other side of the equation, then it is in divided form. Then a into adjoint of a into det a equal to I. This is equation number 1. A into adjoint of a can calculated a into adjoint of a. Two matrices multiplication, by using this two matrices multiplication is there, and by using the definition of a, determinant of a, then we say that the determination by finding the first row with first row, then the value is det a. This value is a1 a1, b1 b1, c1 c1, and the determination finding by using the second row, then value is this, and determination by finding the third row, the value is a3 b3 c3 c3. Then by substituting that values and also the properties of a determinant, ninth property is that this a1 a2 plus b1 b2 plus c1 c2 value 0, and also a1 a3 plus b1 b3 plus c1 c3 value also 0. Similarly, the remaining terms are also 0. Here we can take determination as common, then determinant of a into a 1 0 0 0 1 0 0 0 1. Here this is nothing but a unit matrix or identity matrix, then that is denoted by capital I. Then det a into I. This value is a into determinant of a is equal to det a into I. Here we take cross multiplication, then a into adjoint of a by det a equal to I. This is the first equation we have to write down. Next, then this is the first equation. Similarly we can find adjoint of a into a. Adjoint of here in by finding the first equation, we have to first calculate a into det a. By calculating a into adjoint of a, by calculating a into adjoint of a, we have derived the first equation. And also similarly, by calculating adjoint of a into a, that is we have adjoint of a into a value also det a into I. Then from this we say that adjoint of a by determinant of a into a is equal to I. This is equation number 1. This is a similar term. By the same process of the above multiplication, then we can write similarly. Then from equations 1 and 2, we can derive that a into adjoint of a by det a is equal to adjoint of a by det a into a is equal to I. This can be formed by using the equations 1 and 2. Then we can say that a into adjoint of a by det a equal to a adjoint of a by det a into a is equal to I. This is a derivation of the by using the definition of a inversion of a matrix. By the definition of inversion of a matrix, if A is invertible, then there exists a matrix B such that AB equal to BA equal to here AB equal to BA equal to I. If A is invertible, then there exists a B matrix such that AB equal to BA equal to I. This is a definition of a invertible matrix. By using that definition, because this definition is taken here because A is a non-singular matrix and also A is invertible. Given that A is not equal to 0, that means A is non-singular, and also A is invertible. A is invertible. Then by the definition of inversion of a matrix, we can say that inversion of a matrix A we can say that we can say that adjoint of A by det A, or determinant of A or det A is both are equal, is inversion of a matrix, is inversion of a matrix A. Definition of invertible, here invertible matrix of A, we can say that adjoint of A by det A is inversion of a matrix A. That means inversion is denoted by A invert. A inverse equal to adjoint of A by det A. Adjoint A by det A. This is the proof of the theorem. We have to show A inverse equal to adjoint of A by det A value. This is the most important problem of public exams for 7 marks. For 7 marks purpose, this is the most important problem. Thank you for watching. For more videos, please subscribe my channel and like, share. Thanks for watching our video. For more videos, please like, share, subscribe to our channel and hit the bell icon.